What is going on, guys? Welcome back to another video. Sorry if my voice is a little bit raspy, feeling a little bit cold today. But in this video, I want to take a look at the variational autoencoder paper. So, I think I'll make a future video sort of explaining it more, I don't know, in a more digestible way perhaps, and make it more compact with slides and stuff like that for explanation. But sometimes you just want to go sort of to the root of the source of the information, where you can really feel like you understand all the details of it and understand where it comes from and things like that. I feel like that's really something that's been valuable for me. So if you're interested in starting to read papers, this can be a guide, a way to make it perhaps easier to start reading this paper. I'll also make, in the next video, I'll make a from scratch tutorial where we will implement this in PyTorch. And in this one, it's actually quite simple to implement. I would say that most of what's difficult is actually understanding the theory. And I think you will have a good understanding of sort of the general gist of variational autoencoders and how they work and stuff like that. And you'll definitely understand the implementation video and like have a good idea of the theory. So I guess I'm assuming here kind of what autoencoders are, because variational autoencoders kind of come from autoencoders. Maybe I'll make a video on autoencoders as well, but it's pretty simple. Where the idea is to sort of, you have some input, some nodes as input, you have some some neural network, I don't know, like a couple of layers like this, until you have like a bottleneck layer, let's say with, I don't know, 2 nodes, and then you'll do some more layers, and then you'll have the same amount of nodes as you did in the input. So this is the output, this is the input, right? You probably know what this is, but so this is just some bad explanation of an autoencoder. You have some input with some number of nodes, you do a neural network, you have some bottleneck in the middle, which is having a lot less nodes than in the input. And then the idea is that you can, from this bottleneck layer, reconstruct the input such that the output should approximately equal the input, and you have some loss to sort of ensure that this is the case. In this way, you can compress information. So autoencoders are really good at, you send some image, you can compress it, and then you have the neural network sort of decompress it. And in that way, maybe you can, you can send images to people, but you can compress it, and then they can decompress it on their local device, and sort of the neural network can compress information much more. And there are some interesting applications of autoencoders. But the problem is that it's very difficult to generate new and sample from this because it's deterministic. So variational autoencoders wants to make this probabilistic, such that you can actually use this to generate new samples. And how they do that is actually that they map the input to a distribution onto a distribution of some latent space that you can then sample from or generate from. So now that you have some idea you probably had before, I suggest you check something else if you want more information about autoencoders. But that's sort of the background. Like we know about autoencoders, they're used for compression, but now we want to be able to use some other to be able to sample from it probabilistically. So the abstract here, what they want to do, how can we perform efficient inference and learning in directed probabilistic models in the presence of continuous latent variables with intractable posterior distributions and large data set? So let's try to understand what they actually mean about that. So first of all, Here, X is actually the output, and then we have Z, the latent space, is the bottleneck layer. So what they mean here when they say, you know, this, they want to learn this probabilistic model in the presence of continuous latent variables with intractable posterior. So we have this, we want to have this probability distribution over the output of images parameterized by some weights, theta. Using Bayes' theorem, we then have the likelihood is like a probability distribution of X given theta, which is how well can we, like given the latent variable, can we reproduce the input, basically. So the thing here is that we can compute the likelihood and we can compute the prior, but we cannot compute the posterior in this case. Basically, given some output, we don't know exactly how the distribution over the latent variable is that gives that output. So this is intractable. And basically, you know, what they want to figure out in this paper, how can we do all of these three? How can we compute these three so that we can compute this, and we can do that efficiently, so that we can actually, and we can do this probabilistically. So that's what they want to figure out. So they mention here, we introduce a stochastic variational inference and learning algorithm that scales to large data sets and, under some mild differentiability conditions, even works in the intractable case. So they solve the problem, basically, by doing, they do that by having a re-parameterization of the variational lower bound, which, I mean, we'll get to that. Then when we do this re-parameterization, we can actually optimize this using this stochastic gradient descent methods. So we can use neural networks and so on. And then they also mention here, posterior inference can be made especially efficient. So let's skip the introduction here, basically say the same thing. For the method here, what they want to do here, they've tried to explain or show in this figure where we have some, so they say here, the solid lines denote the generative model, where if we look at X, for example, to generate X, we want to have the latent variable Z, and we want to have the parameters, theta, of our neural network to be able to produce it. But then the question is, how do we get Z? Well, we use the input, which, I mean, the input and the output should match, right? But we use the input X together with some parameters phi to get the latent variable Z. So here we have that the generative model is based on the solid lines, and the, what do they say? The dashed model. The dashed lines denote the variational approximation, Q. So they denote that as Q. Because we mentioned previously that the posterior distribution here, Z given X with this P of theta, is intractable. What they do, and they'll explain that later on, is that they just substitute it with another one, Q, with parameters phi, and they basically want this Q of phi to approximate P of theta. So that's the idea. But all right, so I mean, the problem, right, is basically that we have some data set of images. What we want is that we are able to send this image in, and then we get the image back, right? We compress it into some latent space, and then we can be able to generate. But we also want to be able to generate many different samples from that one probabilistically, so it's not a deterministic mapping. So the first step here, they mention, is a value, Zi. So for example, I is generated from some prior distribution. So we have some latent variable, and then we have that the value xi is generated from some conditional distribution. Now we'll get to that, and they mention that later on, but what we basically see here is that from the latent, we get the image. So this will be one neural network, and what this will do is basically it will decode the latent variable sort of from the bottleneck layer it will get us back the original image. So this is called a decoder because it decodes the compression. What they want to do here also in this paper is they want to not make simplifying assumptions about the marginal or posterior probabilities. Maybe someone can help with this, but I'm thinking what this would mean is that they don't make assumption about sort of conjugate pairs or stuff like that on the prior and posterior, but rather want to just solve it in a general sense or have a general algorithm that works. Where when they don't have this when they have intractability, where we can't compute the integral. So there are some methods that one can use where you can compute this integral, but they want to assume that they have a general algorithm where it works even in this case, and then also that it's efficient enough so that you can use a large data set to actually do this. I don't know if this is too important. They just mentioned sort of that they want to solve it in a general way. And then also what that means, what they want is that they want to have a way of efficiently basically training this thing to get the parameters data, and that this sort of the parameters data will then allow us to mimic the hidden random process and generate artificial data that resembles the real data. So we can generate from it. And also that we want to have some efficient approximate posterior inference so that we can do fast compression. Now, what you can actually do when you then have this sort of, if you have this method or this pipeline, you can do some pretty cool things. Like you can do image denoising, you can do inpainting, and even super resolution based on how you decide the input and the output. So for example, I don't know, you could imagine that you have sort of an image of a digit like MNIST. So you have image here of, I don't know, let's say you have image of a 0 like this for MNIST. What you do is that you have some algorithm for noising it. So you have a noisy 0. And you send this through your VAE and you get some output. And the idea is then that this output should be the the unnoisy or the denoised one. So you use as input, right, this part where you send the noisy 0 to the VAE, but for the loss when you train this, to reconstruct the original, you compare it to the one that you had originally. So that's image denoising. You can also do image inpainting, where you can do stuff like, I don't know, you can like remove a specific region here. You can make that black so that the model doesn't know what is for that one. And then you can ask the VA to basically fill it out. So you could imagine, I don't know, like one example could be like you have some type of mark on that part of the image and you want to not, like a watermark or something, and you want to remove it, you could do that. And also super resolution if you send in some lower dimensional and then have some larger, but I don't think VAs are that good for super resolutions. So denoising and inpainting, and yeah. All right, now what they do is that they introduce this Q, what they call the recognition model, which is an approximation to the intractable true posterior. So they have denoted this by having another set of weights phi than the theta, which is for the actual sort of the true formula should be. But the idea is that it should approximate it. And then they mention here, we'll introduce a method for learning the recognition model jointly with the generative models, a generative model with parameters theta. So they have, basically, you will have the same thing as for autoencoders. You will have this, which will be our encoder, and then you will have, let's see, and then you will also have, with the theta, which is b theta of x given z. So you'll have the encoder. All right, we haven't really gotten to anything that's too interesting yet. But they also say here the recognition model Q is a probabilistic encoder, and that P of theta is a probabilistic decoder. Now, for the dimensionary variational bound, I think this is a little bit difficult to understand actually, and they haven't actually gone through the details of derivation. I don't think I will do that either, but I'll give you the idea of how you actually do it, and I can link a resource that explains it, where you can go through if you really want all the details, but it's not that important. But let's read here. So the marginal likelihood is composed of a sum over the marginal likelihoods of individual data points. So basically we have n data points. We want to take the log of each of those, right, that's outputted. And what we do is that we sum each individual data point individually. Now here, what they do here is that this log of the probability distribution of some particular data point can be written as the KL divergence between this this Q and this P of theta of Z given X, which we can't compute here, but basically they've skipped but they skipped a bunch of steps here anyways. But that basically, just assume now you can write this as this and some other stuff. And I'll explain. So what they did here is that, or I mean, how you come to that is that you start from this formula here, and then you basically take the log of both sides. Having the log, you can do some like place it into different, use some logarithm rules and place it into some different terms. And then what you can do is you can take an expectation over Z. As you can see, the left-hand side is not dependent on Z. So you can do that on both sides. Take an expectation of Z that is generated from Q. And then you can see that that follows the definition of the KL divergence. And then we have this KL divergence, which we got from doing some tricks on Bayes' theorem with taking logarithms and taking expectation and so on. And the details are not too important, but you get to this point here and you have this other L here, which can be written, all right, as another KL divergence. And here you see the expectation. The expectation is still there. The expectation is in the KL divergence definition, but here you can see the expectation I was talking about. So, but here we have an expectation over this. So, and you can see here, this is the likelihood, right? The log of P of theta X given Z. So basically we have these three terms for this log of P of theta that we want, right? And obviously what we want here is that we want to maximize this because we want our outputted samples, right? The outputted images that we get to have high probability in this distribution of images. So the thing here though is that this KL divergence here cannot be computed because we don't know this term here for the P of theta of Z given X, right? That's why we substituted it for Q of phi. So what we can say, however, and they say this here, this KL divergence is non-negative, which means it's going to be greater or equal to 0. And since we want to maximize this, we can instead look at some type of lower bound. So we can optimize the lower bound instead. So what they say here, the second term is called the variational lower bound on the marginal likelihood of a data point I. So we instead look at this thing because we know that the entire thing is going to be lower bounded by this. And those have terms that we actually can compute, right? So here, if we would understand, so this will basically be like, this is what's important, and this is what we will use for our loss function later on. But so what we have for this is this term here is a reconstruction loss. So basically you compare, you can do this in multiple ways, but you just compare what did the input say and what did the output say. Maybe you can do sort of a mean squared error type of thing, or there are multiple ways of doing it. We can look at that in the implementation. But so this is reconstruction, and then you have this thing, which is a form of regularizer, they call it, where we want to ensure that our encoder here follows the distribution that we've set on the latent variable. And so in this case, what that means is that we will push the encoder to output values that are Gaussian. So that's what we will push it towards with this KL divergence. So the regularizer is by pushing the latent space by pushing that the latent space should be some specific distribution. All right, we want to differentiate and optimize the lower bound with respect to both the variational parameters phi and the generative parameters theta. So we use both. We use both neural networks for this because we have we use the encoder and the decoder. However, the gradient of the lower bound with respect to phi is a bit problematic. So the problem now that we come to is that we have this phi, but the problem is that so the problem here though is that so this phi, this encoder that we want to basically we're gonna want to put this x into some distribution, right? But then what we also want to do is that since we want to make this probabilistically, we don't want the deterministic one, right? That's what we had for our encoder. What we want here is that we want to be able to map this particular point into a distribution on a latent space so that we can generate from it. The problem is when we let's say it's Gaussian, if we sample from a Gaussian distribution, it's going to be non-differentiable. So we can't compute the gradient for that. So we're going to have to use a trick, which they're going to mention later on. But for now, they just say it's a bit problematic. All right, now let's see. So here they come into the idea of what you can do instead of sort of sampling from the Gaussian distribution, right? And again, why we want to sample from the Gaussian distribution is because we want one single image to be mapped onto a distribution of points so that we can get many different variations from a single input so that we can actually generate. That's the idea. So here they say, under certain mild conditions outlined in section 2.4 for a chosen approximate posterior, we can reparameterize the random variable using a differentiable transformation G of an auxiliary noise variable. So they don't go into specifics of how they do that here, but just the idea that what we can do is we can reparameterize, so we get some Z out from the encoder network. We can then use another function G, which uses some epsilon, that's some randomly generated noise, and we can use that to get a new Z tilde. So the idea here is basically that what we will have later on is sort of a function that takes this Z that's deterministic and then makes it random by using noise. So it's pretty cool, and we'll get to how they do that later. But let's see here. So what they do here, let's see. Yeah, here this is not important. It's basically just that you can take in, actually skip it. It's not important. We can skip this. And yeah, so this is the same thing here that we saw previously, just that the Z here is going to be generated using some noise. So it's not just the Q, it's also generated by noise. So yeah, we'll skip this. We'll get to the important part. So here they have some algorithm showing how it works. And also why I ignored this, by the way, is because they set L to be 1 anyways. So it doesn't, this thing doesn't matter. But yeah, so here they have theta and phi. They initialize parameters. So that's the neural network. They draw some mini batch. They generate some noise, epsilon. This is, I mean, I wrote pretty unclear because this is just some general algorithm, right? Then we compute our loss, the gradients with respect to our loss, and we update parameters. I mean, that doesn't really say anything. So the only thing that's valuable here is that L is set to 1, which means that this thing here doesn't really matter. The only thing they mentioned here is like you can take an average of the output when, because like the latent is random, right? You can generate many different, and then you can take an average. But yeah, it's not what you do in practice. Often the KL divergence can be integrated analytically. So this is the good thing. The regularizer part of the loss that I mentioned. So we have the regularizer term and we have the data reconstruction. This is not, this is something that we can compute. So it's going to be an analytical solution. And let's go down. Let's see, a connection with autoencoders become clear when we're looking at the objective function. The first term is the KL divergence of the approximate posterior from the prior, acts as a regularizer, while the second term is an expected negative reconstruction error. So we talked about that. Now we get to the actual trick. So how does this actually work? And this is the Re-Parameterization trick. And remember, this is to solve that we can sample from a particular distribution, but still have it differentiable so that we can do gradient descent. So here they say the essential parameterization trick is quite simple. It is then often possible to express the random variable z as a deterministic variable, where epsilon is an auxiliary variable with independent marginal p of epsilon and g of phi is some vector valid function parameterized by phi. Basically, all they say here is that, yeah, the noise is separately generated. So we have a deterministic Z, and then we use some random noise to make it into a particular distribution. Here, they say, take, for example, the univariate Gaussian case. Let Z be some normal with mean mu and sigma squared variance. In this case, a valid reparameterization is Z is mu plus sigma times epsilon. So here, if you choose epsilon, all right, so if you do that with Z, then this will be normal with mean mu and sigma squared. So, you know, basically what you can imagine is you have some values mu, and then you just plus that with some values sigma, and you multiply that with this epsilon, which is that, and that's the only thing that needs to come from a normal distribution, right? These two doesn't have to be normal. As long as you do this and you multiply it with this, it's going to be normally distributed. So that's the idea. Pretty simple. But in this way, you can actually sample from a particular distribution, Gaussian in this case. And they also show that you can do this for other distributions as well, but Gaussian is going to be the most common one. All right, it's going to be a long video anyways. So here the example, variational AutoEncoder. In this section, we'll give an example where we use a neural network for the probabilistic encoder. So the example here, they let P of theta be a multivariate Gaussian in case of real value data, or a Bernoulli in the case of binary data. So it will be a multivariate Gaussian for us, for images, and then whose distribution parameters are computed from Z with a multilayered perceptron. Yeah, basically just that we use a neural network for it with linear layers. But yeah, I think that will be clear in the implementation video. All right, we'll assume the true but intractable posterior takes on an approximate Gaussian form with an approximate diagonal covariance. So what they do here is that they, I don't know, maybe someone can let me know why you need to make this assumption on the diagonal, having diagonal covariance. what would be the problem with not assuming that? Might be that it's computationally more expensive somehow. I'm not really sure. But anyways, they'll assume that it's covariant. So what this means is that the latent space for Z, basically the variables are independent. So that's a strong assumption, I think, but it seems to work anyways. What that basically means is that, if we have a latent space of two variables, then like if you increase this one, like if you increase one of them, then the other one is not going to increase. Like it's not, that they're independent. So I don't think that makes sense that it would be the case. However, you can look at like, there are cases where you have a disentangled latent space, for example, for VAEs, but also for GANs, where you're able to make a latent space where, like, for example, you could have that if you increase the first one, then the output person in the image has glasses. And if you do the second one, then the person smiles, and so on. So you can imagine that you can have that they can be independent, but it's not that you assume that they're going to be feels a little bit strong in the assumption. But anyways, so they do that, they assume that. And here, so the mean and the standard deviation are outputs of the encoding MLP. So I don't think they have a figure actually, but what you have is that you have your image, you send it through your encoder. So this is a linear layer with that you'll see in the next video as well, but it's just linear layers. And then what you output is like a vector of values, which is the mean, mu, and another, which is the standard deviation, sigma. And then this is used with the parameterization trick to multiply it. As you can see here, we sample from the posterior Q with this G function is this mu, which is outputted from the linear layer, plus this standard deviation, which is outputted from the separate linear layer. So, this is one linear layer, this is one linear layer. And then they do an element-wise product with noise, where the noise is generated from a normal distribution. Because it's element-wise multiplication here, then that means that they are independent. But I'm thinking you should be able to do some other operator here that doesn't mean that they're independent, so that you don't assume this, you don't have this strong assumption. But I don't know where that would break. Anyways, what we said earlier is that, so we have this L, right, which is the lower bound, variational lower bound that we want to optimize, because there was one term that we couldn't compute. And that for the regularizer term, that was a KL divergence, we could compute that analytically. Now, they might have that in the appendix or something, but basically you get this thing right here. When computing, you just plug in the definition and you do, you compute the integral, you get a closed form solution, which is this. So, what this means, like the intuition here for just the first term here, for the regularizer, is that, remember, we want to maximize this. So how can we make this as large as possible? First of all, we can make the mean 0, right? Because we're subtracting that. So that's what we want to push it towards, the latent space, mean of 0. And then we can also, if we make the standard deviation 1, we'll have log of 1, which is 0. And then we have minus 1 squared, which is 1. So this entire term becomes 0. So it's just an intuition that it makes sense, I guess. that what the analytical solution is makes sense, that it also pushes it to be standard normal. So, now you might be asking, well, if you push the mean to be 0 and the standard deviation to be 1, won't that do nothing? But you need to remember also here that we have the second term, which is the reconstruction loss. So this mean and the standard deviation also has to contain information about the original image so that we can actually reconstruct, we can use this and reconstruct the image. So there's a balance between these two. And that's why they also say here, somewhere, approximately diagonal covariance. It won't be exactly because we push it towards that, but then we have this other term. So this Z here is going to be mu plus, we talked about that. All right, so that's it for the important stuff, I think. So basically what happens if we remove this stuff here, so what happens is that we have this mu and sigma. We compute Z by doing this element wise with epsilon. So we generate epsilon here. So here we generate this epsilon by doing from like a standard normal distribution. After we have that, we can use this set and we can send it into our decoder, and we get an image. And this image at the top should equal the image at the bottom. But the pro thing, or the good thing here that we solved by doing this, is that this is a probability distribution, because we have this random thing here that we can do multiple variants of. So we can generate many epsilon, we can generate many Z, and then we can generate many different types of images. All right, so that's what we solved by doing it this way. Let's see, so we have related work, we have some experiments. I'll skip all of this. Basically, they just show that it works. So here, the conclusion is we have introduced a novel estimator of the variational lower bound. So what, the thing here is that how they come up with this, like the theory of how we should estimate it. The loss function, basically, with the KL divergence for the regularizer and the reconstruction loss. They don't actually say specifically how you do the reconstruction loss, for example, but it should be, you can do like a mean squared error or binary cross entropy, for example. All right, then they say this stochastic gradient VB, SGVB. I get lost with their abbreviations, I'll be honest. I don't know exactly what they mean with this stochastic gradient VB. But they say for efficient approximate inference with continuous latent variables. I guess it has something to do, with the parameterization trick of how you compute Z using this, what they call, this G function. I think that's probably what they refer to here. But basically that you can do efficient inference for the image. And then that you have proposed estimator can be straightforwardly differentiated and optimized using standard stochastic gradient methods. And they do that by utilizing their Re-Parameterization trick, because you can't sample from the distribution and still have it be differentiable. All right, hopefully that made sense. Hopefully that was useful in some way, and you can look at the paper in more depth if you want. But hopefully now you have an understanding of VAEs, you understand where the theory comes from. Maybe not understand all of the details, but you know where to go and look at. And basically have a good sense of what it is, right? Like the only thing we didn't look at, for example, what we would look at to really understand all the details is first of all, if you use a log here, what are the steps so that we get the KL divergence terms? But it's basically just logarithm tricks, and that's it. So it's nothing difficult, it's just some work. And then the second thing we didn't go through is, what else did we not go through? Yeah, we also did not go through how this thing here is computed analytically. So we didn't, but this should be a simple, this is from the definition. So it should not be something difficult. But so anyways, just some work. with that, I think you have a solid understanding, and you can definitely follow now the next video. All right, thanks for watching, and I hope to see you in the next video.